In classical control theory, engineers rely on a comforting assumption. The physical system we are trying to control, the plant, remains static. Any disturbances to that system act independently. We call this a linear time-invariant model. Push a vehicle past Mach 5, and that assumption disintegrates. The friction from traveling over a mile a second superheats the surrounding air, generating temperatures up to 3,000 degrees Celsius and encasing the vehicle in a sheath of atmospheric plasma. At these speeds, standard mathematical models collapse. The physical properties of the airframe itself are constantly morphing under extreme aerothermal loads. To survive this environment, these vehicles require precise geometry. Every curve is highly sensitive. A single millimeter of thermal warping drastically alters the aerodynamics. To keep a hypersonic weapon on its intended trajectory, engineers have to tear down the standard feedback loop and completely rebuild it to handle severe, compounding uncertainty. The control system's internal logic acts as the primary governor for the vehicle's structural integrity. This diagram represents the standard single-input, single-output control loop. In the middle sits the plant, the mathematical representation of the physical missile. In a hypersonic scramjet, the mass drops drastically as the engine burns through its fuel load. The inertia tensor shifts violently when a glide body separates from its rocket booster. The aerodynamic coefficients are highly nonlinear, shifting continuously with altitude and Mach number. The main plant equation splinters into dozens of shifting variables. Then there is structural flexibility. Massive aerothermal loads physically bend the vehicle's metal control surfaces mid-flight. Countering these forces requires strict material constraints. It takes massive, solid metal test articles just to simulate the physical strain of this coupled structural heating on the ground. Because the physical plant is uncertain and constantly shifting, relying on one textbook transfer function guarantees catastrophic failure. The environment at the beginning of a hypersonic trajectory shares almost no physical characteristics with the environment at the end of it. This chart shows the flight trajectory. During the initial boost phase, the vehicle is low in a dense atmosphere with strong aerodynamic authority. During the early glide phase at the peak, the atmosphere is extremely thin and aerodynamic control drops to near zero. A controller calibrated for dense air at Mach 3 will force the vehicle into an uncontrollable spin at Mach 7. Engineers solve this through gain scheduling. They linearize dynamics at dozens of operating points, establishing strict stability margins for each specific condition. The flight computer dynamically switches or interpolates between these localized PID controllers, using real-time Mach and altitude sensor data to select the correct tuning. But gain scheduling has a critical vulnerability. The transient moments between states, especially during violent physical events like booster separation, can introduce sudden instabilities. When basic interpolation isn't trusted to survive those violent transitions, engineers rely on an advanced mathematical framework called Lyapunov stability analysis. This graph visualizes a Lyapunov function, a mathematical construct used to prove a system is safe. By designing the controller so that the system state strictly descends toward equilibrium, the vehicle is guaranteed to remain stable, regardless of the specific trajectory it takes. By defining this mathematical safety envelope to bound the system's behavior, engineers use a logic shared by autonomous AI agents, which apply the same Lyapunov framework to remain within safe limits, even when encountering unpredictable data. Stability margins are not theoretical safety buffers. They define the strict physical bounds in which the hypersonic vehicle is allowed to exist. In a typical control model, disturbances are treated as isolated, random inputs. A sudden gust of wind shear here, a spike of thermal noise there. In hypersonic flight, a single factor acts as a correlated disturbance that degrades multiple systems at the exact same time. Extreme aerothermal friction physically warps the vehicle's structure, while simultaneously generating a sheath of highly ionized plasma around the airframe. That plasma sheath completely blocks incoming GPS satellite signals. For the entire duration of the glide phase, the primary feedback loop is severed. Without GPS, the control system has to rely entirely on its internal inertial measurement unit, processing data from high-speed onboard gyroscopes and accelerometers. The fatal flaw of an inertial unit is that it accumulates errors, causing measurements to drift rapidly. Without GPS to correct it, This drift compounds. Within minutes, the internal position estimate diverges hundreds of meters from the actual physical location. To bridge the gap when the sensors go blind, engineers implement a Kalman filter, an optimal state observer. The observer uses an internal computational model to constantly predict where the missile should be, filling in missing data. It mathematically fuses this predictive model with the drifting IMU readings, calculating the truest possible estimate of the vehicle's state. When physical reality is obscured by plasma, the state observer creates an internal mathematical reality. That computation allows the control loop to survive. Environmental disturbances are only half the problem. A military vehicle faces intelligent, adaptive adversarial inputs, like GPS spoofing and targeted radar jamming. These electronic warfare inputs are purposely engineered to inject false feedback into the system and actively destabilize the control loop's error signal. The protective solution is a dedicated countermeasure loop that actively identifies and isolates hostile signals before they can corrupt the main navigation data. This diagram shows the final nested architecture. You have an inner guidance, navigation, and control loop handling the physics, a middle electronic warfare loop protecting the sensors, and an outer mission computer guiding the overall reference path. A modern hypersonic control system is a defensive architecture, meticulously designed to protect the integrity of its own logic. We've gone from a fragile, static equation to a highly robust, gain-scheduled, state-observing nested architecture. Testing this architecture exposes a harsh reality. No wind tunnel on Earth can perfectly simulate structural bending, acoustic shock, and plasma denial all at the exact same time. Actual flight tests carry enormous financial and operational risk. It requires massive infrastructure, like modifying a B-52 bomber just to deploy the test vehicle, all to validate the control logic in the real world. Because physical ground testing is always incomplete, the theoretical robustness of the control design serves as the absolute final line of defense. Control engineering is the vital discipline that translates abstract differential equations into the guaranteed physical survival of a Mach 5 system.